Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 4, Section 1, Part 1. So, Part 1, well, actually, all of Chapter 4 is on physical and chemical change. And then Part 1 is about understanding chemical changes. Some essential questions you should be able to answer at the end of the chapter is, what is the difference between physical change and chemical change? What kinds of chemical changes are there? How do we recognize chemical changes? Okay, so question for you is, we have ice and we have liquid water. Is this still the same substance? And have the physical properties changed? And can water go back to being ice? Another example is paraffin, so 2C20H42 solid plus 61 oxygen molecules will react to form 42 water vapor molecules and 40 carbon dioxide molecules. So over here, is this the same substance and have the physical properties changed? Can you get it back? Once you burn the wax, can you get it back? Nope. So water can go back into ice, as you know, because you've probably frozen water. But you cannot take some carbon dioxide and some water vapor and just make a candle out of that. So the atoms, not only have they moved around, like the molecules have been moving around, but the atoms themselves, so like the carbon reacted with the oxygen to get carbon dioxide. So the atoms were rearranged, and this change is irreversible. A chemical reaction has occurred. So please write that down, chemical changes. So chemical changes are a change in the molecule themselves, and it is irreversible. Unlike a physical change where you could just put it back, you could just refreeze the water. And this change affects the composition of the molecule of a substance and makes a new substance with different properties. So in our wax example, when we burn the wax, the water vapor and the carbon dioxide does not have the same properties as wax or oxygen. Right there. Combustion of paraffin into carbon, water vapor, and carbon dioxide. So this is just a little bit of soot left over. Any of that black stuff would be just leftover carbon. So please write down the equation. 2 molecules of paraffin, C20H42, that start out in the solid, a solid candle, react with 61 oxygen O2 gas molecules to form 42 water vapor molecules and 40 carbon dioxide molecules. Okay, so a chemical change will break the strong bonds between atoms in a molecule. Those are the interatomic forces, so the forces between atoms. Previously, we talked about intermolecular, the forces between two molecules. And so just like I said, the physical changes break the weak bonds between molecules, those intermolecular forces. So if we have a physical change, the water, the H2O molecules in ice could break and become liquid ice and kind of flow over each other, or water vapor and zip around, but they're still H2O and H2O. Whereas if I had a chemical reaction and I decomposed water into oxygen and 2 hydrogens, I would have oxygen and then hydrogen, and these would be totally different things, and the bonds between the oxygen and hydrogen of water would have had to have broken. Those interatomic forces. So most chemical changes take more energy than physical changes because you're breaking those bonds between atoms, which are really strong, compared to the forces between molecules, which isn't so strong. Let's look a little bit more at physical and chemical change. So in a physical change, the molecules are rearranged, the intermolecular forces are broken, and those interatomic forces stay together. So we've got one water molecule, H2O, and that intermolecular force between another molecule, H2O, breaks, but not these strong bonds between the atoms. So in a chemical change, we know the atoms are rearranged and the interatomic forces are broken. So you actually break the bond between the oxygen and the hydrogen itself. So we can see that physical changes don't take as much energy as chemical changes. All right, so you need to take some hypothesis. You need to make some predictions. So we've got rock candy, granulated sugar, and confectionery sugar. And turning from one to the other, is that a physical or a chemical change? And then adding food coloring and having it diffuse throughout the solution, is that a physical or chemical change? If you said physical, you are correct. Good. All right, so we've got some oil and water, and then vigorous mixing, and then we get a dispersion of the oil in the water. Is that a physical or chemical change? If you said physical, you are correct. The oil and the water are still there. And another question I have is, can we obtain any arrangement of atoms? Can we have O2, H2O, and H2, so we know those are real things, but could I have H3O or H4O? Nope. Each type of atom allows only certain chemical bonds to be formed. This is due to the structure of the atom. So please write this black stuff down. All right, so looking at the structure of the atom, we know the structure of the, well, I'll just leave myself down. We know the structure of the atom is important on what molecules it can form. So let's look at that. So an atom is not like a hard ball, like a billiard ball or like a pool ball. It has this like diffuse electron cloud around it. So most of the mass is in the nucleus, but the nucleus takes up just a teeny part of the whole volume. So I've heard the analogy, if this was like a football field, there would be just like probably like a paper clip or a dime or something in the middle, and that would be the nucleus. All right, atoms. Please write this down. Nucleus has protons and neutrons and nearly all of the mass. Protons are positive, and the number of protons is the same as the atomic number. Electrons are tiny negative particles that surround the nucleus, and they are found in the electron cloud. The number of electrons is the same as the atomic number if you have a neutral atom. We'll get into ions and all that later. So atoms are neutral because the number of protons equals the number of electrons, and we know that protons are positive, electrons are negative, so when positive charges equal negative charges, it's 0. All right, so looking more at the structure of the atom, the number of electrons corresponds to the atomic number of the element, because we know protons equals electrons, and we know that the number of protons is the same as the atomic number. How many protons does bromine have, and how many electrons does bromine have? So please take a look at your periodic table to answer that question. So we have hydrogen, and hydrogen has an atomic number of 1, and it has 1 electron. 1 proton, 1 electron. And then you have helium, which has an atomic number of 2, so it's going to have 2 protons, and it has 2 electrons. Lithium has an atomic number of 3, it has 3 protons, and therefore it has 3 electrons. Okay, so we've all seen pictures of atoms when they have those little orbitals where the electrons are zipping around, and that's not really how electrons go. We tend to have this diffuse electron cloud, so this is a little bit more realistic. And we know electrons have a negative electrical charge. So if they are negative, how could an atom even stay together? Because we know that the protons are repelling each other in the nucleus, and the electrons are repelling each other in that electron cloud, but we know that the protons and the electrons are attracting each other. So it is balanced out. But why don't all those negative electrons just like fall right into the positive nucleus? and it is a balancing of forces. So just like the Earth is attracted to the sun by gravity, it also has its motion, which it wants to go in a straight line. So if you take those two forces together, you get an orbit. So just like that, an electron is pulled into the nucleus, that positive nucleus, but it also has momentum to kind of go straight. So when you put those two together, it kind of zips around in that electron cloud. All right, so let's write about chemical bonds, please. Each element has a unique number of electrons and arrangement of electrons around the nucleus. So the electron is the particle that's really involved with chemical bonds. So we were just talking about the electron because it is part of chemical bonds, and that's our segue. This gives each element its unique chemical properties and determines what bonds the elements can make. So electron is the name of the game for the element's properties and what chemical reactions or molecules that element can form with. So a chemical bond is when electrons are either shared or transferred between two different atoms. So donated, accepted, or shared. So let's take a look at some electrons and chemical bonds. So we can see that some electrons, well, we know electrons, all of them are responsible for chemical bonds and chemical reactions, molecules forming. So they could be transferred. So when I have a sodium ion, it actually wants to give up its electron and then become positive, and it gives it to chlorine, which becomes negative, and then the positive and the negative are attracted and you get an ionic bond. The electron was transferred. Over here, we might have, let's say, part of oxygen and hydrogen, and then maybe there would be another hydrogen over here to make water. Those electrons are actually being shared between the two of them. So it's not like one gives the other, but they share it, and that's called a covalent bond. Okay, please write this down. We were talking about making charged particles, making positives and negatives, and forming ionic bonds. Well, that means an ion would be involved. An ion is an atom that has lost or gained an electron. An ion is going to be negatively or positively charged. And our two examples we went over were positively charged sodium, which lost an electron, and negatively charged chlorine, which gained an electron. So just like I said, sodium lost an electron, chlorine gained an electron. Always remember this is a small l, not a capital I. So we know the electron was transferred. And then that attraction between a negative ion and a positive ion is a bond that we call an ionic bond. So ionic compounds are going to form crystals and not molecules because the ions are attracted to all of the surrounding ions. And we'll look at a picture of that. So it's different than like just one water molecule. So we'll look at a picture of that in a minute, but I do want you to write some more stuff down. So an ionic bond, and you want to keep this in your head because it's going to keep coming back up, is when you have a metal and a non-metal. So something on the left side of the periodic table and something on the right. I think that's flipped for you, sorry. But your left and your right. Metals on the left, non-metals on the right. And then when they come together and make a compound, we call that like a salt. So not just sodium chloride, but any metal and any non-metal together making an ionic bond is called a salt in chemistry. So potassium sulfate, potassium chloride, lithium, oxide, these are all salts. Okay, as promised, here are some pictures. So we can see that these blue sodium ions are actually attracted to not just one, so it's not like a molecule of just a sodium and a chlorine. It's attracted to all surrounding chlorine. So there, down, and if it was in the middle, up and coming out this way. All right, so we're going to talk about covalent bonds in our next video. I'll see you then.